I'm Thomas, Breed's product marketing manager. At Breed, we think the battery development process is too opaque. We think critical data and insight is locked behind supplier walls. Silo teams makes it too slow to get access to the answers and context needed. And quite frankly, there's just a lack of expertise in the industry, which adds more bottlenecks to the whole development process. So we built Breed Design. Breed Design is physics-based cell design software. It's made to get you the answers you need to develop battery-powered products fast, efficiently, and with confidence. Today, I'm going to show you what Breed Design is, how it works, and what happens when you can create virtual cells. Feel free to check out the chapters and jump to the topics that interest you most, or stick around for the full video.
So I'm going to start by opening up a Python notebook. And that's because Breed Design is a Python-based API. And we built it as an API, so it's flexible and extensible to the needs that you might have for your workflows in your context. Has the added benefit of being compatible with the powerful new AI coding tools. And what we provided with the API is the core functionality, so that we've handled lots of the main workflow pieces, so you don't have to worry about coding. You'll see lots in this examples, and the subsequent examples are one lines of code, because we want it to be super easy to use and really easy to get the functionality out of it, but giving you the ability to extend on top. So I'm going to start by importing Breed Design into my workspace, importing it just as I would any other Python package. And if you're not familiar with Python or these sorts of things, don't worry, we have you covered with lots of great documentation and worked examples for using Breed Design to do to get to the sorts of outcomes I'll show today. So I'm going to walk through in this chapter just the really core functionality of Breed Design and the core workflow that we'll then build on top of in the subsequent examples to drive even more unique or more applied solutions. So my account has access to the P45B, the Moly cell, good old reliable. And what I'm going to do is ask Breed Design to get the design parameters for that base battery, which for all the demos will be the Moly cell P45B, and then I'm going to print them out. You can see when I run this, what I get back is a list of design parameters. All these design parameters come from Breed's battery lab in London, where we parameterize the cell and validate and update them to the API backend. And so what this means is, you would send us a cell that you already have or know or are familiar with, and we parameterize it, and you can start working and reimagining it to your new system context from there. So what I'll do is I will give Breed Design, I'll ask it to get the equilibrium KPIs for that base battery. What that means is I'm giving Breed Design this recipe, those cell design parameters of electrode thicknesses, chemistries, etc. And I'm going to ask it to provide the predicted performance in a static use case. And what that means is it's going to use Breed's physics-based, one of the many physics-based models that power Breed Design, the equilibrium model, and calculate with those parameters, what can I expect? And what we see here is we can see predicted capacities, nominal voltages, energy densities, masses, heat capacities, etc. So I have these two items now. I've got my design parameters and the performance I get for those design parameters. But now what I want to see is the sensitivity of the performance to those design parameters to get a feel for where I might want to go next with this cell. And we can see one of the other outputs from this function called get equilibrium KPIs was the sensitivity figure. And again, with the APIs, we've built in a lot of the workflow, so you don't have to add much code. You can see lots of this is very minimal code to get you going. And when I plot that sensitivity figure, just by running that, I can see I get my KPIs along the bottom, my design parameters along the top, and I can start to see if I want to, for example, change the gravimetric energy density by reducing the NP ratio, by increasing my maximum voltage limit, by increasing my electrode thicknesses. Those are all kind of the main ways I could do this. And so foreshadowing here, I can start to see that the mass is going to, as I reduce my NP ratio, I'm actually going to reduce my mass. And same if I increase my anode and cathode thicknesses, I'm actually going to increase my mass. So let's take a look at what that looks like. Here's how easy it is to change designs and reimagine the cell with Breed Design. I'm going to create a list of new designs. I'm going to call one thicker electrodes, and I'm going to increase the base design's cathode thickness by 20%. And I'll do the same for the anode. For my second design, I'm going to lower the NP ratio. I'm going to take the base design and reduce it by 5%. I think the base design is about 1.034, if I get the number right. So 5% off that. So I'll save this. And what I'll do is go back to that get equilibrium KPIs function call once more. Provided my base battery, the Moly cell, along with now this list of designs, and print the results. And so you'll notice I did things like increase the electrode thickness. And if you only increase the electrode thickness of your model, but then thought about conceptually rolling up that jelly roll to put it into a can, if you're rolling up a thicker electrode, it's not going to fit in the same size. And that's one of the really powerful features of Breed's equilibrium model, is that when I increase the thickness of that electrode, it's actually going to decrease the overall length of the jelly roll to keep it consistent. So we call this physical consistency. And so when I virtually roll up that jelly roll, it will still fit perfectly into that 21700 cell. Inversely, when I lower the NP ratio, I'm actually getting a longer, it's going to adjust the parameters accordingly as well. And we see this show up in the mass here. So as I foreshadowed in the sensitivity piece, actually get a slightly lower mass than the baseline, which is the first column, to the thicker electrodes. So yeah, I've actually reduced the mass slightly. And that shows up when we compare the gravimetric energy density of the thicker electrodes to the lower NP ratio. We see that while the lower NP ratio has a higher capacity, it's actually added some mass here. So on a gravimetric basis, it's slightly worse. But on the volumetric basis, because they're both the 21700 format, it's actually better. So again, because the API builds in some of the core functionality to make it easy to use, we've created some plotting features because a table is sometimes hard to tell that story. So what I'll do is breathe design plot KPIs, and I'll just pass it the data from this table. I'll ask for the delta, which means the absolute value difference in these KPIs. You can see here, I have in dark green my thicker electrode design, and in light green my lower NP ratio. We can see that impact, and the delta is all from the baseline, by the way, so that's what the zero axis means. So you can see the weight's gone down with the thicker electrodes, as I mentioned, and the weight's gone up with the lower NP ratios. And then we can see when we compare our energy densities on a volumetric basis versus gravimetric basis, we see an inverse story. And this is really cool because this is when we start to see how your system application is actually really important for this right cell for you. If your application that's really sensitive to mass, then the gravimetric energy density increase, even though it has a lower capacity on the spec sheet, would be better for you versus the volumetric energy density. And this is how you can use breed. This is the starts of the seeds of how you can use breed design to set the direction for your R&D, for the cell suppliers you engage with, for requesting changes from the cell supplier, because the right cell for you is the right cell for your system, and only you as the system developer has that insight. So that's a quick overview of the static KPIs. But what's really interesting is that you can also do dynamic simulations with breed design. And what that means is those new designs we generated, we can export them to a format for breathe model to use, which is a single particle model with electrolyte, thermally coupled. If you don't know what that means, it's a physics-based model. So it means we get insights to the internal states of the cell, like anode potential, to do some fast charge assessments. But then we also get the common cell voltage and heat generated and cell temperature and things like this. So I increased the thickness of my electrodes, and that's looking good at gravimetric energy density. But one downside of increasing that electrode thickness is I would expect that I'm going to make the resistance slightly worse. And again, this is where the application and the use case is really important. But if I am a high power application, then on paper, higher capacity might actually result in lower runtime if my route to the higher capacity was a higher thickness. So because I have high resistance, because then under my high load, I'm going to hit my voltage limit sooner, and I'll have a cutoff there. So being able to do these dynamic simulations is really helpful to understand, impacts on thermal management systems if the temperature increase goes up, what the anode potential during fast charge might be if my resistance is changing and that runtime is changing. And I'm going to do a pretty simple thing here and just do some DCIR pulses. And I'll use that as an assessment to see if these designs are good enough for me or not. So I'm going to use Breethe's built-in cycler class, and I'm going to interact with the cycler class in units of C rate. And I'm going to define my 4.5 amp hour nominal capacity for that C rate, which is the nominal for the MolyCell P45B. I'm then going to request Breathe Design to run a simulation using the base battery as the reference with my new designs. And for the cycler class, I'm going to request a DCIR pulse. So I could use CC discharge, CCCV cycling, CC charge, etc. But for here now, I'm just going to go for DCIR. And I'm going to look at a 1C discharge pulse for 30 seconds. That's what those first two values are. And this is just 5 seconds on either side with my voltage limits. And don't worry about memorizing all these parameters. Again, we have documentation to keep you moving quick, and you can refer to it at any moment. We're going to do this pulse from 70% SOC at room temperature. But again, flexibility. If I'm a high temperature use case, I actually might want to be specific to the pulses my system might expect, to the temperatures it might expect, to really tailor this result to me and the information I most need to move forward with designs. So I'm going to run this. And yeah, so what's happening in the backend is Breathe Design has been sent these designs, and the simulation is being run on Breathe server side. So nothing on the machine. And again, one function line call, api.runSim, and we get some dynamic simulations that are running in the Simulink environment. So we don't have to worry about managing setups or tuning solvers on my laptop. I just get the answers I need, which is what is the DCI of this cell. And I skip all the fiddly bits. So I'll plot this, again, using Breed's built-in plotting, Breed's plot dynamic response, and I'll give it the data and ask for the cell voltage. So we can see here the simulation that was run. I have my 3 lines, the dark green baseline, and the gray lower NP ratio design, and the white thicker electrode design. So for those of you who might not aware, I can kind of expect already that I'm going to have a slightly lower resistance with the lower NP ratio design because the voltage drop is less than the baseline and the thicker electrodes one. And we can confirm that by using another one of Breed's built-in functionalities, extract dynamic KPIs. So I can say, here's the raw data. I want the DCIR. Let's see. And there we go. We see over that 30-second period, the baseline had 17.7 milliohms of resistance. The thicker electrode increased that to 20.4, and the lower NP ratio actually reduced it on the baseline. So now I've got the ability to have the insight and the information and the context I need to make confident decisions of, if I was working with cell supplier, requesting, for example, hey, can you understand what the impact of lowering the NP ratio would be? This increase in energy density and decrease in resistance would be really great for our system to, maybe we have thermal issues, or maybe we have some runtime issues during high pulses, we hit voltage limits, etc. And finally, I can download these designs. So if I request for Breed Design to download them and I provide the designs, it'll actually export and download to my machine the 3 different designs, the baseline, the thicker electrodes, and the lower NP ratios. And what I can do is then go into Simulink with Breed's model and simulate, just as I would in my workflow for system simulation, what this performance would look like. So that's really cool if I already have a packed simulation or a module simulation or a mini module simulation built up with the cell that I already know. I could say, okay, if I tweak that cell a bit, how would that same simulation work? So if I had track racing or simulations for AI workloads on my consumer electronics device, for example, when it's cold, I can see what the impact on these greater system level performances would be. And so that's kind of how we see the overall workflow of Breed Design being. It's that connection from that electrode design at the very start, making some changes to the cell design to optimize that performance more, and then actually getting the context of what it looks like on system level by moving into Simulink from there. All right, so picture this, just launched a new product and it's time to start thinking about the next generation. And there's some requests for it to support some new features. Maybe it needs to be thinner and maintain the energy density because form factor is key. Maybe it is that it needs to support more AI workflows on device, and that means more power requirements. Or maybe it's that it needs more range on a vehicle because the class that the product is in is being demanded for more range, or even lower cost, right? Whatever it may be. And these are the sorts of things that Breed Design can help out with. So let's jump in. And I'm going to open up my Python notebook again. And we're going to think about 2 scenarios here. First one is silicon a route to get the answer I need? And if so, how much silicon do I need? So I'm going to start by importing Breed Design. And we're going to use the Molicel P45B as the base here. And in the previous chapter, I showed how easy it is to change some of the geometries and things like NP ratios or thicknesses of electrodes. And with the exact same workflow, you can just as easily define chemistry compositions. So in this case, I'm going to design 3 silicon chemistries, or 3 silicon blends, and these are all weight percentages. And scenario here could be that we go to the same cell suppliers, or we go to suppliers that we work with, and they say, yeah, we have the ability to do 3 different silicon weights. And we might want to understand what that means for us and which one is right for us, because with silicon, it's great at adding energy density. It's also great at adding more problems to development and more risk. We all know it swells a lot. We know that the rate of graphite loss and silicon loss is not equal, so that might have challenges for control and estimators. And it'll be costly too. It's a more novel technology, less established than graphite, so the cost of higher silicon too needs to be worth it. So there's a balance here of what's really needed for this next product. So what I'm going to do is I'm going to look at first at a 5% silicon by weight again. These are all by weight percentage, blend with graphite. And you can see here, all I have to do, define my anode as my graphite and silicon ratios. And 5% kind of the entry point to silicon, let's say, in terms of the addition you would add. 8%, a little bit more, but still quite established these days. Quite a few cells on the market that support this sort of ratio. And we can see again, super simple definition of how we do this. And then finally, let's say there's a bit more of an experimental option here. It's 15% silicon. And maybe not super experimental. There's definitely products on the market that have this, but it's definitely on the say the higher edge of mass production. And I know there's things out there 35% plus of silicon, and that's awesome. That's possible, but yeah, let's just hypothetically stick to this. So I'm going to save that list of designs, and I'm going to come to my equilibrium model. So I'm going to ask Breed Design with the base batteries, the Bowling Cell P45B, to also take those new designs into consideration and predict what the static KPIs would look like. And this is great because then I don't need to rely on the time it takes to interact with cell suppliers and getting information back and forth. I don't need to take any cells in to do any sort of testing or characterization for this. And I don't have to worry about scattershot information available on spec sheets. I get all consistent information when I need it, as I need it. And so let's print those results. So we see the baseline here. This is the existing P45B, 4.5 amp hours. A bit outdated now, but the cell's old, so that's all right. I know Moly sells some great new offerings. And we can see the jump already with that 5%. We're jumping to 5 amp hours, which is a bit more modern. With 8% going to 5.5, and 15% we're actually going over 6 amp hours in capacity, which is really cool to see. We can see how the nominal voltage here is changing. This might change some of the calculations we might do for some high level estimations of power availability and energy. We can see the energy calculations here actually. You can see that corresponding increase above 20 watt hours on that 15% one. And yeah, equally, you can see the mass is actually being updated and the predicted mass is changing. And that does show up a bit in the gravimetric energy density changes, though it's still increasing with silicon content. So yeah, this is really cool because maybe, based on the high level estimations of what these new features I need or what the new demands are for this new product, I know 18 watt hours was actually the target. And I can see here that 5% silicon is going to give me what I need there. And I don't have to worry about the cost and complexity increases of pushing for higher silicon and going for 20 watt hour cells. This is not actually what's needed. This was hypothetical, but it shows sort of the ways you can get really quick answers out of Breed Design. And especially in these early stages of development, it's really important to start off on the right foot because you might not know that, hey, actually 15% was too much or too complex or unneeded, or vice versa. Maybe you actually needed the 20 watt hours and 5% doesn't get you there. And it's only throughout the development process where layers of performance are abstracted, or you need to do those optimizations and energy might reduce and new problems arise, that you could have these delays in development and you need to go back to your cell supplier and work with them again, or maybe you need to consider a different chemistry altogether and things like this. So it's really important to start off on the right foot, and Breed Design is a great tool to give you the data you need to do that in the context of your system, which you hold. I changed silicon here, but we also equally could have changed the cathode to an LFP chemistry and done some cool things there. So yeah, not just limited to silicon. Another example, maybe I'm developing my next battery fits for a vehicle, and I'm considering, I've heard lots about 4680, I've heard lots about the BYD Blade, big prismatic cells, and I'm trying to work out, is it worth me redeveloping my platform? Because there's a cost if I change my cell format. I need to change the form factor, change the platform architecture and everything to get to use these new ones. And again, instead of working with cell suppliers and there's all the chemistry might change as well alongside the form factor and all these other nuances. And again, about status shock data sheets, I can get all that information in Breed Design and get the prediction I need to move forward. I'm going to do this example in an automotive context, but this would also work for consumer electronics, where you might want to have different options available in terms of how much space in the device is allocated to the battery and changing and fitting it there. So I'm going to start by defining two form factors. The first one is going to be a large prismatic cell. I'm going to call it prismatic. I'm going to say the casing is made of aluminum. Housing thickness, so how thick is the casing? And then I'm going to make it 22 centimeters by 11.5 and then 30. So quite large. And I'm going to say it's a stacked jelly roll type. And for those of you who aren't aware, stacked means that the jelly roll sheets are like sheets of paper stacked on top of each other. And what that means is, as the prismatic is a cuboid, the rectangular sheets make the most of all the space. Conventionally, you might see more wound jelly rolls, and what that means is you're taking a round object and trying to squeeze it into a cube, so you get some energy density loss on the corners. Sorry, a bit of a deep dive there. And I'm going to compare that to the improvements I get with the 4680. I'm going to call it 4680. The material is going to be steel, and the housing thickness, 0.5 millimeters. This is in line with the Tesla design. For those of you who aren't aware, sorry, I just used the term 4680. That's a cylindrical cell, so it's a cylinder can with 46 millimeter diameter, 80 millimeter height. And I'm going to define the inner diameter, which is actually the jelly roll, the gap in the middle of it, to be 5 millimeters. Again, this is in line with the 4680 that Tesla uses. So I'm going to save that to a list, and I'm going to go back to my equilibrium model. So I'm going to API get equilibrium KPIs, and I'm going to give it the base battery once again. I'm not changing anything with the chemistry. This is the base moly cell electrode designs, and I'm going to give it the formats that I outlined above. What's really cool is, again, because Breathe Design is a physically the equilibrium model that's in Breathe Design is physically consistent. When I give it that 4680 format, for example, and I give it that 5 millimeter internal diameter, it's going to wind up that jelly roll with the exact same design, porosities and thicknesses and all these things to fit into there, and to do that calculation for me, so I don't have to worry about any of that. And just like that, I've turned the moly cell P45B into a large form factor prismatic cell and a 4680. And so with the exact same chemistry, I can see what performance differences I get. You can see, for example, the energy density is quite a lot higher. And this could be really interesting in terms of maybe, it would be worth taking the jump there and changing. I can see the predicted mass. So this might be interesting when I think about my application. If I was to scale this to the voltage I need, what's the mass that's going to get, mass impacts I might have, and if that's right for me. I can see some heat capacity prediction, so I can do some high-level calculations there and understand what it might mean for the thermal system required. But we can see things like the nominal voltage hasn't changed because, again, we're not changing the chemistry. Yeah. So again, just set off on the right foot with the battery world, as is one of the reasons I love it. There's, what's right and what's conventional doesn't really exist. 21700 has been around for a while. What's right chemistry to use? We hear LFP, NCA, NMC, these new novel LMFP chemistries and things like this, and navigating this world to find what the right battery for you is challenging, because if you get it wrong, this could mean lots of delays. It means building up technology stacks to support them, like platforms, like estimators, and the initial choice of what to do from the onset can really have these big knock-on effects. So Redesign is a tool to help make sure that first step is data backed and in the right direction. So for this last example, I want to do two things. The first is I wanted to show the sorts of workflows that Breathe Design can enable for those who are in environments where custom cell development isn't feasible or possible, or where the leverage of the cell supplier is maybe limited to or non-existent. And the second is I wanted to show the sorts of extensibility and flexibility to build solutions on top of Breathe Design, because it's an API. So what I did is I built a Python notebook that makes use of the cell design changes in Breathe Design to invoke cell-to-cell variation. And what I did is built some functions on top of the design parameter settings that puts distributions on these values. And this is important because no battery cell is the same. Batteries are designed to extreme precision, but there's such a quantity of them and the volume at which they're made that no cell is exactly the same, and this impacts the performance metrics. And therefore, when you're shipping your battery products, the performance should not be seen as a single value, but needs to be seen through the lens of probability and distribution within allowed values. And so if you're building your battery product and you're still buying cells off the shelf, those cells are still going to contain a degree of variation. And with Breathe Design, you can build workflows and build tools that account for this variation to make sure that you have visibility over the performance of your products and that your user experience, but also robustness and resilience to this by building it into your design and development workflows and validation workflows and simulation to ensure things like state estimators and controllers are resilient to this cell-to-cell variability. So what I've done is imported Breathe Design and created my own package of Monte Carlo utilities. And this is, again, an example of the sort of solutions that you can build on top yourself, or you can work with Breathe to build solutions that address your needs. I'm going to take the moly cell P45B and get the base parameters in base design. Then in these base designs, I want to impact 4 design parameters for now. I'm going to look at anode and cathode porosity and anode and cathode thickness. And what I'm going to do is apply this distribution. So I've defined a Gaussian distribution, so bell curve, and with a nominal value being the base design. And this is, kind of in line with how manufacturing quality tolerances can be expected. And I'm going to clip the tolerance at plus or minus 3.5%. And just like in manufacturing, you'd have a, rejection qualification criteria on some of these measurements. And what I'm going to do is randomly sample 75 different designs from these distributions that are applied to each parameter. You can see what that looks like here. I have this of the different design parameters I have, the different distributions I get. And now what's cool is I can predict what performance I can expect out of this. So I'm going to look at the equilibrium KPIs, the static KPIs, and from them, I want to look at the capacity. So not only am I getting the range of capacity I could expect, but I'm also getting the probability of this capacity occurring. And this is helpful because, it might be extremely costly to account for super end state values. And it might be more likely to, you might have your own expectations on ppm and quality standards in your own products that you need to account for. This can also be helpful for deciding how to, grade batteries to put into your products, and designing systems around cell sorting. And again, because we can do dynamic simulation with Breathe Design, I'm going to do DCI pulses because these parameters that we're changing are going to impact the resistance as much as they are the capacity. And it's an unknown what that distribution will look like, so I want to simulate it. So I'm going to do a 1C discharge for 30 seconds, and I'm going to run for all 75 different combinations of designs. And we can see that took 3 minutes and 20 seconds or so, which is probably about the time it takes to load a single cell into a jig if you're super fast. So if you think about, to do this in a testing environment, you would need 75 cells. And often cells come from the same batch and from the same lot. So that distribution is like localized to that. So you have less visibility than you would over, a larger sample spread. So this not only gives you the ability to get a more of a global view, it also lets you do it super quick. And you can iterate on this really fast as a result. So I'm going to use Breathe Design's built-in extract KPIs functionality. And then I'm going to plot this histogram results. And we can see it's less of let's say Gaussian distribution from the number of samples I've chosen here than the capacity one. And I can actually map that capacity to resistance and use that as a proxy for the sort of cell quality I can get using this heat map. And what we can see here is some interesting pockets. We see there's a kind of zone in the top left where we see the higher resistance and the lower capacity coupled. We see there's the capability for a low resistance but nominal capacity. And we see the kind of clustering in the middle and the sort of resistance ranges we would expect. I can hover over each one of these and get the exact design that resulted in that if I am interested to extract certain ones. And from here, it can just keep going, right? I could start simulating rate capabilities around here to see if I'm at risk in low temperatures. And I could start doing fast charge cycling or fast charge simulations to start seeing if my anode potential is at risk. And I can even export all of these designs. And maybe, like I said, I can hover over and pick outliers or pick common distribution ones and use these simulations to build up packed simulations with cells that represent a realistic variation, a realistic distribution. I can refer back to that probability to populate my packed simulations with this, or I can check my validations if I'm doing SOC estimation. I can extract some of these different edge cases, common, less common, super boundary condition like this one over here, and take a look at the accuracy impact I might get on my SOC, because in theory, this is a cell that would go into production because it passes the criteria from the supplier side. And as a result, make sure that the user experience is guarded. So that's a look at just some of the things Breathe Design is capable of. We took a look at the core workflow the API enables, some of the exotic changes you can make, like chemistries and form factor adjustments and predictions, and then built some solutions on top of the API to address cell-to-cell variation and envisage some workflows that you could enable to build resilience to cell-to-cell variability in this world where you can create virtual cells. If you'd like to learn a bit more, see some other use cases in action, get in touch. Or if you have any battery problems that you think a solution on Breathe Design could help solve, we'd love to hear more from you and talk about potential partnerships. Thanks for watching.